We will continue our discussion on entropy method and present the so-called log-Sobolev inequalities. We have been seeing that if one can establish bounds uh, for this quantity, the divergence between Q of um, so if we can establish bound for entropy of e to the power lambda f by the moment generating function, and this quantity we saw is actually a divergence between our tilted measure lambda f and the original distribution p. So if we can establish bound for this guy, if we can show that this is less than equal to say some lambda square v by 2, then the log moment generating function for this random variable x here is less than for this random variable f of x is less than equal to again lambda square v by 2. Okay. And yeah, this let's do it for only lambda greater than equal to 0. So we'll get one-sided Gaussian tail bound, right? If we can show this, and then that was the first part of the entropy method. This is called Herbst argument. And second part is a tensorization property, where we saw that actually this ratio, this entropy of e to the power lambda f by the moment generating function, when you have IID random variables, can be bounded by something very similar to F-Einstein inequality, expected value of similar quantities, but now described by fixing all but the ith coordinate. Okay, that's the second. This is the tensorization part. I think this was done 2 lectures ago, right? Lecture 8, and this is what we saw in the last lecture. Okay. All right, so this is just essentially a property of this divergence. All right, so now, so what this allows us to do is to in order to establish a bound like this, you can establish a bound on individual quantities. But how do we establish bound on these quantities? And that's where log-Sobolev inequalities enter. Now, log-Sobolev inequalities had existence, a very rich and successful existence before they were applied to concentration modes as well. And so we can first present those inequalities without showing how they can be used for concentration mode. So I'll start with this so-called binary log-Sobolev inequality. And then we'll use it later to derive the so-called Gaussian log-Sobolev inequality. Just like we derived Gaussian Poincare inequality from a binary version of that Poincare inequality. Okay, that's the plan. So let's start with this. So this is a very specialized inequality. Let x equal to x1x and be uniform on -1 to the power. Okay, so this is the uniform distribution on the binary hypercube. So called this set is called the binary hypercube. Uniform distribution on the binary hypercube. Okay. So in particular, x1 to xn are independent, and they're all Rademarker. Next, let f be a function on this binary hypercube. So it's a function from -1 1 n to r. So recall that entropy of any function is defined as expected value of f log f minus expected value of f log expected value of f. Okay, that's what entropy of this function is. So the binary log-Sobolev inequality that we plan to show looks like this. Binary log-Sobolev inequality. There are other similar related inequalities, but the one we want to show is the following. Entropy of f square is less than equal to entropy of f square is less than equal to summation I equal to 1 to n expected value variance I f. Okay, so we can name this guy. This is 2 times ef, where ef is sort of the energy, but we'll call it ef is the Afrenstein. I'm just making this term up. Variance estimate, not a very formal term. So this is basically the right side of the Afrenstein inequality. So this ef. So remember, if you recall your Afrenstein inequality, this guy here can be written as expected value given all the past of f of x minus f of xi, f of x, maybe I'll write it more detailed, f of x1 to xn minus f of x1 to xi minus 1, replace I with the ith independent copy, and xi plus 1 to square of this. Okay, this is exactly what the variance is given all the other entries. Okay, so that's what this binary log-Sobolev inequality will show, that this entropy of f square is less than this. So before we prove it, let's see concentration on concentration bounds. Let's see how to get concentration bounds from binary log-Sobolev inequality. So this, of course, this is just an example, and later we'll extend it to other distributions as well. Okay. So what we will do is we'll apply this inequality to the function. So consider f from -1 1 into r, but we will not apply binary log-Sobolev to this function and define. We'll apply it to, remember, we have to look at entropy of e to the power lambda f. Apply it to e to the power lambda fx. Okay, bx by 2. Then by binary log Sobolev inequality entropy of G, which is entropy of G square, which is entropy of e to the power lambda fx. This entropy is less than equal to summation I equal to 1 to n expected value variance given everything of e to the power lambda fx. Okay, and this quantity actually, this e to the power lambda fx, this is a quantity we had seen earlier. Remember when we were deriving earlier, we had shown when we were deriving concentration bound using Afrenstein inequality, we saw that this quantity here is less than equal to, see lecture 7, I think. So used in deriving concentration bounds from Afrenstein. Let me check what lecture was that. Was it 7? Yeah, 7. Right. So we saw this inequality. This quantity here, this is our variance, and we saw that this guy is less than equal to. So there you had lambda by 2, but here we now only have lambda is less than equal to variance z minus zi prime times this y square. This guy here. So what we showed this guy here is actually, sorry, this entropy of this is less than equal to variance of this by 2. By 2 remains. So we have entropy of f square is less than equal to variance. So by 2 remains. So now that earlier bound that we saw, that one, that's why this y by 2 was required. That gives you each guy here is less than lambda square by 4 in the same expected guy. Okay. E to the power lambda fx, this is the bound we saw earlier, times fx minus f minus 1 so I think the notation that we used there was so the z was fx and zi prime is equal to f of xi minus 1 xi prime xi plus 1 2. That was the notation we were using for reference time, but that's quite convenient. So what we get is e to the power lambda z minus zi prime square, only the positive part of this. Okay, so that would have been a factor of half. Yeah, this is what we get. And therefore this guy here, this is, we had seen it earlier, this is just a Taylor series approximation bound, but very nice. So what we get is lambda square by 4 expected value of to the power lambda z summation I equal to 1 to n z minus zi prime square. So now suppose, this is the assumption from earlier, suppose that summation I equal to 1 to n, this z minus zi prime square is less than equal to v to v almost surely. Okay. Then, so this is our assumption. That's what we also had in this bound. So just to refresh your memory, you can go back and check. So again, here again we were assuming, the assumption was that we were deriving this kind of concentration bound. So this guy here is less than equal to v. So now we don't have this plus sign. So that's from symmetry, that's 2v. So this was less than equal to v. So this is less than 2v, and we got this kind of bound. Now we'll see that this bound gets improved using entropy method. Okay. So this is less than equal to v, 2v. Suppose this is true. So this is our assumption. So then under this assumption, this previous bound here for entropy of lambda fx, this guy is bounded by v. Then entropy of e to the power lambda fx is less than equal to lambda square by 2v times expected value of e to the power lambda fx. And this implies that the ratio of these two, which is the divergence between q lambda f from p, is less than equal to lambda square by v, and which by Herbst's argument implies that the log moment generating function of fx is less than equal to, so you can have fx minus, those two log moment generating functions are the same. I mean, the ratio, you can subtract the same quantity and nothing changes. So you can show this is less than equal to lambda square v by 2. Okay, so that's great. So what we have shown is a sub-Gaussian bound. Earlier we were not able to get the sub-Gaussian, we only had a sub-exponential bound. If you're worried about this part, the only thing I'm claiming is that if you subtract minus expected value of x from here and here, nothing changes. That's sort of a homogeneous function. Okay, it's easier to see here. In the tilt, you can subtract it from both numerator and the denominator. Just a constant multiply with both of them. So fx is greater than expected value of fx plus t is less than equal to e to the power minus t square by 2b. Okay, that's the Gaussian concentration bound that we were looking for. Earlier we only had t by root v. So that's great. So this is, we only did it for this Rademacher, this uniform distribution on the binary hypercube. But at least this illustrates how this log-Sobolev inequalities of this kind, if proved in some way, note that it was not straightforward how to use it to get a concentration bound, but we used some elementary inequality and we were able to get this quantity here from e to the power lambda fx. This is roughly Taylor series approximation. Okay, so I hope I've convinced you that there is some way to connect these inequalities to concentration bound, and that's the recipe of entropy method. Now it only remains to prove this inequality, the binary log-Sobolev inequality, which just claims that entropy of f square for any function f is less than equal to this guy here. This is very similar to the this is exactly the 2 times the Efrenstein variance estimate, which is sort of the energy in f, or sort of the fluctuation in f. I think it's better to think of it as a discrete gradient norm square. So keep Gaussian-Poincare inequality in mind, and this is a discrete counterpart of that, of the expected value of the gradient norm square. Okay, so what remains to be done? So we still have to proof of, we convinced you, hopefully I convinced you that this is useful. The binary Sobolev inequality is useful, but let's prove it now. binary log Sobolev inequality. Okay, so how do we show this? So first we notice that so we have to show that entropy of f square is less than equal to summation I equal to 1 to n expected value variance given everything of f. Okay, that's what we have to show. So first step is tensorization step. So by the tensorization of entropy, we note that entropy of f square is less than equal to summation I equal to 1 to n expected value entropy of f given everything but the ith coordinate. That's the conditional. You can call it the conditional entropy of f square. Okay, that's the first step. Okay. And so suppose hash holds for n equal to 1, then this entropy of f square here is less than equal to variance expected variance. So there's nothing to take expectation over in this case because all the other guys are now fixed. So for n equal to 1, there is no additional expectation. This expectation is over the remaining coordinates. Okay. So then this holds for every I. Therefore we get what? Therefore, entropy of f square is less than equal to summation I equal to 1 to n expected variance I. Okay, so this is how we were able to use tensorization of entropy to reduce this binary log-Sobolev inequality to only one-dimensional case. So how do we show this one-dimensional inequality? And that's the second part of the proof. The n equal to 1 case. And this is some elementary inequality we have to show. So what is this inequality for n equal to 1? We have to show that entropy of f square, so think of just a function of a single bit now, entropy at g be a function from -1, 1 to r. Okay. So we can just say that, say, g of -1 equals to a, g of +1 equals to b. Then entropy of g square, it's for n equal to 1, is equal to a square is expected value of g of the function. So expected value of g log x. So with probability half, g takes the value a, so you get a log a. Then with another probability half, g takes the value b, so you get b log b. Minus g square, sorry, so a square log a square, b square log b square. And then minus, what's the average of what's the expected value of g square? That's a square plus b square by 2 log a square plus b square by 2. That's the entropy. And we would like to show that this guy is less than equal to, there's something to show. So now to show here. So this guy is less than equal to the variance of g. So what's the variance of g? So that's variance of g is it's a with it's a minus a plus b by 2. Yeah, so I guess you know what the answer will turn out to be, but let's just write it into b minus a plus b by 2. These are both b minus a by 2 square. So this is just b minus a by 2. So with probability half, this is the mean. With probability half, you take the value a, you get this. Probability half, you take the value b, so you get this. B minus a by b minus a square. And 4. Okay, so this by 4 looks a bit wrong to me. I think, okay, so maybe I'm missing a factor here. Right. So the binary log-Sobolev inequality that I guess we would like to show, maybe it has a this variance is correct. Maybe we need a factor of 2 here. Yeah, let's just put a factor of 2. See how it looks. This is 2, so we can show this times this. So that becomes by 2. Yeah, this one is the one I think we can show. Okay, so how do we show this? So one interesting thing here is that this inequality, this inequality is an elementary inequality and just involves 2 numbers. So what we have to show is that this function hp of a, which is given by say half a square log a square. So I'm thinking of it as a function of a for a fixed b, is half b square log b square minus minus a square plus b square by 2 log a square plus b square by 2 and minus b minus a square. So what we have to show is that this function is less than equal to 0 for all a and b, but we can put further restrictions. First thing you notice is that if a and b, first thing is that without loss of generality, we can assume a greater than b. If you show it for a greater than equal to b, then by symmetry it holds for a less than b also. And the next thing is that you can assume that both a and b are of the same sign, and that sign is positive. So if they're of the same sign, then positive or negative doesn't matter. So they're both of the same sign. And the reason we can do that is if they're of different sign, then you're subtracting more, and it's a smaller quantity. So this is the region in which we have to show this inequality. So we notice that hp of b is equal to 0, and then you take this derivative and notice that its derivative also is 0 at b. Okay, that's something you can check about hp. The function is 0 and its derivative is also 0. Okay. And then you can check its second derivative at any point, and the claim is that the second derivative is actually negative, okay, non-positive. So this for all a greater than equal to b. So this implies that hb of a is less than equal to 0 for all a greater than equal to b. So I didn't show this proof, but this is something, this is an elementary inequality, you can verify this. Alright, so this is the magic of tensorization. It allows you to convert this sort of sophisticated looking inequality into an elementary inequality. So we have seen this. So I missed this factor of 2, but it won't change too many things here, I think. It's just a constant factor of. So when you bring in this factor of 2, I think everything will still work out. All right. So to conclude, we have shown the binary log-Sobolev inequality, and we also saw how that binary log-Sobolev inequality implies a concentration bound. Okay. Next, what we look at is so where is this? In main part of this thing is this binary log-Sobolev inequality. Now, recall that earlier when we were deriving Gaussian-Poincare inequality, we actually derived it using a similar Poincare kind of inequality on the Boolean hypercube. Okay, and that's something we will do again. So since we have binary log-Sobolev inequality, we can now use it to obtain the Gaussian log-Sobolev. How do we do this? So to get the Gaussian log-Sobolev inequality from its binary counterpart, we proceed as before. So let so let it's the claim of the Gaussian log-Sobolev inequality. Gaussian log-Sobolev inequality says that this is the theorem. Be a standard normal random variable. What is that? That's n0i. Okay, independent component channel, um, all with unit variance. So let this be a standard Gaussian random variable, and let f be any function from this Rn to R such that it is continuously differentiable, just like we had in Gaussian log, continuously differentiable. Okay. Then what we can show, and we can show this by very similar steps as before. Maybe we need more assumptions of some boundedness of second derivative, continuously differentiable with bounded second derivative. Maybe that's that check, something to check. That's the condition we used when we derived the Gaussian Poincare inequality. I think that may still be needed because we need a Taylor series approximation in the middle. But then the claim is that entropy of f square is less than equal to 2 times expected value of gradient norm f square. Okay. This is very similar to the Gaussian Poincare inequality, except that variance has been replaced by entropy. Okay, that's the inequality. This is the Gaussian log-Sobolev inequality. That entropy of f is bounded above by 2 times expected value of gradient of f square. Gradient 2 norm of gradient of f square. Okay. So how do we show this? The proof is very similar to what we did earlier. I'll just give a proof sketch. So step 1 is to first notice that by tensorization of entropy. It suffices to show this for n equal to 1, so one dimensional case. Okay, because this also becomes sum of derivatives. And now step 2 is we consider epsilon 1 to epsilon n. So now we only are showing it for n equal to 1. So we consider epsilon 1 to epsilon n as IID, or maybe epsilon 1 to epsilon m, not n is not a good idea. M, IID Rademacher, random variables, and let g of epsilon 1 to epsilon m be defined as f of 1 by root n summation I equal to 1 to n epsilon I. Okay, and we apply binary log-Sobolev inequality to G. Use Taylor's approximation for f. That's where we require this boundedness of second derivative. I think that will be needed, or at least uniform boundedness of the first derivative will be needed. Taylor's approximation for f. Yeah, I think in this case, because in this case we don't need the boundedness of the second derivative. In this case, it's enough to have bounded first. In this case, I think we are fine. Okay. So let's see. I'll maybe elaborate a little bit. So may not be needed. May not be needed. Okay, let's see. Taylor's approximation for f and CLT at the end. So let's try to do this. So first step is by this binary log-Sobolev inequality. Let's see. Entropy of G square viewed as a function of this m random variables is less than equal to half summation I equal to 1 to m expected value. Now, since this is a uniform distribution, we can write a slightly different form of the variance. That's something you can verify. We can write it as g of epsilon 1 to epsilon m minus g of epsilon 1 to I minus 1. So these guys remain the same, epsilon 1 to epsilon I minus 1. You flip the sign of the ith guy, and then epsilon I plus 1 to epsilon m square. Okay, so this form that I'm putting down here applies only because we have Rademacher distribution, uniform distribution. In fact, we only prove binary log-Sobolev for this distribution, and so that's the reason. So we can expand it. We can do Taylor series approximation around this guy. So if you look at these terms, so this term here is f of 1 by root m summation I equal to 1 to m epsilon I. When we were proving Gaussian Poincare inequality, we didn't have this form. Okay, there was some deviation from both of them, and therefore we had to assume second order boundedness. But here I think we don't need to assume that. So this is f of 1 by root m. We don't have to assume that the second order derivative is bounded. Minus 2 epsilon I by root. So when we do Taylor series approximation, this is less than equal to 4 epsilon I square by m So this part, and the derivative here, f prime 1 by root m j equal to 1 to m epsilon j. Okay, great. Okay, so this implies that entropy of f of 1 by root m, I'm writing it in this form so that you understand what are the random variables we are taking average over, is less than equal to half. So this 4 comes out, so you get this guy also gets squared, so this 4 comes out, so you get 2 epsilon I square by m summation I equal to 1 to m f prime 1 by root m j equal to 1 to m ej square, expected value of that. Now there is no dependence on m on I here, so this is just exactly equal to 2 epsilon I square. So epsilon i's are plus minus 1, so this guy is just 1 by m. This is just 4 by m, so this is just 2 expected value of f prime 1 by root m summation j equal to 1 to m epsilon j square. And now by central limit theorem, because f prime is continuous function and this is also a continuous function, we can take limit of m going to infinity, and in that limit this goes to x standard Gaussian and this goes to x. Okay, and this is where again we use that f is continuous and its derivative is also continuous. Alright, so we get this form, and then we sum it over all coordinates and we get the result. So that's the proof of the Gaussian Log-Sobolev inequality. Okay, and then as a consequence, as a corollary, what we get is the following. So again, x1 to xn, IID, let's say n01, and then f is a function from Rn to R such that f is continuously differentiable and gradient of f, let's say the norm of gradient of f is less than equal to 1. Then we can prove a concentration bound for it. Then probability that fx is greater than expected value of fx plus t is less than equal to e to the power minus t square. Okay, so let's see. I think that's the claim we can show. Maybe a constant is off, but let's try to prove this proof. So how do we show this? So by the way, this condition here, continuously differentiable, this, I think it can be relaxed to Lipschitzness of f using some kernel. So take a Gaussian kernel and convolve f with Gaussian kernel, and you check that this goes to f as n goes to infinity. So basically you start with a Lipschitz function f and then show that for a Lipschitz function f, this guy here becomes nice and continuously differentiable, and this guy will have its gradients bounded by 1, and so you apply this bound for this function and take the limit. Some approximation like that can be done, but let's just show it for this case. That's the main result here. Okay, so how do we show this? So since f is continuously differentiable, we can apply Gaussian log-Sobolev inequality to f, and by applying Gaussian log-Sobolev inequality to f, we can let's see. So let's look at the entropy of e to the power lambda. Okay, since f is continuously differentiable, e to the power lambda f is also continuously differentiable. It's less than equal to 2 times expected value of norm gradient of e to the power lambda f square. So what is the derivative of e to the power lambda fx? That's lambda e to the power lambda fx times this, right? So what we notice is that the gradient of e to the power lambda f, norm square, is equal to lambda square e to the power lambda f. So this should be by 2 because this is entropy of f square. Yeah. So this by 2 by 2 by 2. That's lambda square by 4 e to the power lambda f because you're squared, and then the norm of gradient of f square. Okay, and so this guy is less than equal to lambda square by 4 e to the power lambda f. Okay, therefore entropy of e to the power lambda f is less than equal to lambda square by 2 times expected value of e to the power lambda f, and this implies that entropy to the power lambda f by expected value of e to the power lambda f is less than equal to lambda square by 2, which by Herbst argument, this guy here implies that the log moment generating function of, in fact, fx minus e of fx, you can always multiply and divide by e to the power minus expected value of fx. This at lambda is less than equal to lambda square by 2, and that gives you a Gaussian concentration bound. So this is sub-Gaussian with parameter 1. Actually, we just showed it for one side, so that's why one-sided bound. So you should have 2 here. Okay, and if you have v here, you will get a v here. So that bound, the Lipschitz constant, becomes the sub-Gaussianity parameter. That's the result here. It's a very interesting bound. So it says that if you have a continuously differentiable function with gradient norm bounded by 1, then it has a Gaussian concentration bound with variance parameter 1, and can be extended to, as I said, by using some approximation. Fx to f such that fx minus fy is less than equal to norm x minus 1. So if you have such an f, we have probability fx for such an f, probability fx is greater than expected value of fx plus t, we assume that this exists, less than equal to e to the power minus t square by 2. Yeah, so just as I said, you can approximate this Lipschitz functions by a sequence of um, continuously differentiable functions with bounded gradient norms, and then apply this bound to those functions. In fact, the sequence that I was talking about is just a convolution of, as I said, f and the Gaussian kernel with different means, with different variances. All right, so that's all I wanted to say in this lecture. To summarize, we saw a binary log-Sobolev inequality and extended it to obtain a Gaussian log-Sobolev inequality, which is very similar to the Gaussian Poincare inequality, except that variance gets replaced with entropy of f square. And with that inequality, we were able to, using Herbst's argument, show a concentration bound for Lipschitz functions of Gaussian random variables. So Lipschitz functions of Gaussian random variables are have a sub-Gaussian tail bound, one-sided sub-Gaussian tail bound at least, with actually Lipschitz is a symmetric property, so you can by symmetry also show the other direction. So they have sub-Gaussian tail bounds on both sides with sub-Gaussianity parameter 1, or Lipschitz constant if the Lipschitz constant is n. That's the claim. All right, that's all I wanted to say about say in this lecture. In the next week, I'll give 2 more lectures, final lectures on this entropy method, where I'll use entropy method to derive the where I'll extend now to beyond just this Gaussian random variable or binary random variable to arbitrary random variables, and establish the so-called modified log-Sobolev inequality, which will give sub-Gaussian, which will give similar bounds for general random variables, and not necessarily just smooth functions or Lipschitz functions of Gaussian random variables. That's what we will see in the next lecture. See you next week.